Hello to everyone to the webinar from Metal Toledo. Today I will present the work of Primin Hitber and me, how we optimized a crystallization process using inline FTIR spectroscopy and focus beam reflections measurements. Here you can see the short overview over the presentation. I will start with the background of the work and give a short introduction into the used PIT tools. Before I will show you why we had to put some further effort in the development, how we optimized the crystallization process, and finally the conclusions we get out of the experiments. We received the crystallization process from another site with the mission to develop it into a robust process. The procedure was a seeded cooling crystallization of a high toxic product. It should be tested if it's feasible to omit the seeding by running the process with a spontaneous crystallization. Furthermore, the product should be optimized in terms of filterability in the larger scale. Therefore, we equipped an Optimax reactor with an IR spectrometer 45M and an FBRM. We tried to reproduce the crystallization procedure from side A on our side, but unfortunately we didn't meet the targeted particle size distribution. You can see on the right hand side graphic that our distribution was much broader and it got a big increase in fine and coarse particles. It looks very closely to a bimodal distribution. The distribution overall is less defined and much broader. From this point of view, it can be said that the process was not reproducible and we had to do some further investigations. To find the cause in the different particle size distribution between the side A product and the product of our experiment, we equipped an Optimax reactor with an 45M IR spectrometer from Metal Toledo. We built a model to determine the API concentration at each point of time. We also used the gravimetrical data from solubility experiments in the lab to calculate a polynomial fit that showed the temperature-dependent solubility. Out of these two parameters, we could also calculate the supersaturation at each point of time. To monitor if any unexpected event happened, we used an inline focus beam reflectance measurement to monitor if we have new fine particles or if the bigger particles are also growing. The system works like this, that we have a rotating disc with a lasers. If the laser strikes a particle, the light will be backscattered. The duration of the backscattered light is proportional to the charge length and the speed of the rotating disc. To build a robust model to predict the API concentration out of the IR spectra, we run an experiment where we had the API as a suspension in the solvent. We heated it up to the clearing point, where we knew that now all the API was dissolved and we had a defined concentration in the solution. We cooled down the solution until a point where we saw an increasement of the fines in the FBRM. Then the API was falling out and we didn't know the exact concentration of the API in the solution. Because of the ATR technology of the IR probe, we can only measure the API that is in solution and not the one who is in a particle. When we had the increasement of the fines, we added some further solvent to dilute the API, heated up again to the clearing point and cooled down. We run several cycles so that we could measure at 6 different API concentrations over a broad temperature range. On the right hand side on the top you can see the 6 different API concentrations. So we measured in an interval of 2 minutes a spectra so that we could cover the temperature range. And all the dots of the different temperatures are more or less overlapping because the effect of the temperature is now built in the model. To suppress any baseline effects that could occur, we used a first derivative. So we get a very robust model to predict the API concentration independently of any temperature change. The model to predict the API is then used to measure the experiments. We also used the polynomial fit for the temperature-dependent solubility to calculate the supersaturation. In this experiment you can see that we have a spontaneous nucleation at the point. Then we steered for several hours until the supersaturation was close to zero. After this time point we started to cooling down the suspension, and whereat the supersaturation slightly increased. So we were able to measure the API concentration with the PLS model, to calculate the supersaturation, and also to monitor if we have some finds that are growing or that we have new finds from secondary nucleation. After we built a reliable method to measure the API concentration in the solution, we equipped an Optimax reactor with an IR spectrometer 45M from Metal Toledo and an FTIR to reproduce the procedure from the side A. Then we could see that when we run the second cooling ramp that we had a slight increasement in the supersaturation. At the end of the second cooling rate, we could also see that the supersaturation goes down very dramatically and that the finds in the FTIR increase. This is like indication for a secondary nucleation, which could also be seen in the FTIR where we have an increasement of the finds. We also had a closer look to the IR spectras measured during the experiment, especially at the signal at 1688 wave numbers. The signal decreases during the experiment, shifts, increases slightly and decreases again. A possible cause would be a liquid-like cluster as described in the publication of Roche et al. In this theory, the API gets surrounded by the solvent before it forms a solvate crystal. The interaction between the solvent and the API could impact the carbonyl stretching vibration, which leads to the shift to a lower wave number range. But from the X-ray diffraction, we knew that the desired polymorphic form B was produced, which was no solvate. To optimize the crystallization process, we also changed some other parameters to find the best conditions. To have a look at the crystal grow rate, we changed to different cooling rates from 33 degrees Celsius down to 1.5 degrees Celsius per hour. We also used different amount of seeding crystals, from a few seeds up to 1.5% of the API amount. Furthermore, we used also seeds with different particle size distributions. We used jet milled, hammer milled, and the seeds we got from the side A. In the table below you can see the different particle size distributions of the seeds used, whereas the jet milled or micronized seeds are the smallest. Here you can see the results of the experiment with the fast cooling rate. We had oversaturated suspension, which was seeded and then cooled down with 33 degrees Celsius per hour. In the graphic we can see that when we started to cool down, the supersaturation increased because the grow rate of the API was much slower than the increasement of the concentration. At a certain point, the crystallization leads to a secondary nucleation where the supersaturation was just too high and all the API crashed out. This led also to increasement in the particles measured by the FTIR, which can be seen in the graphic on the right hand side. The experiment with the slow cooling rate was once more seeded and then cooled down with 1.5 degrees Celsius per hour. We can see on the left hand side graphic that the supersaturation stays constant on a very low volume. The whole process took more than 2 days time. On the right hand side we can see the seeding where we had a big increase in the counts of 50 to 150, but then we cannot detect any secondary nucleation or other unexpected events. The crystals just grow to larger particles. Like in the experiment before, we had a look at the signal at 6088 wave numbers. In the experiment with the slow cooling rate, the signal smoothly decreases and don't shows any shift. While on the other hand, the experiment with the fast cooling rate shows again the shift of the signal to lower wave numbers. A possible cause could be that at the secondary nucleation, which occurred with the fast cooling rate, one more time a solvate was produced. From the three experiments, we took some scanning electron microscope images. You can see on the left hand side the experiment with the slow cooling rate, which formed nice particles. On the other hand, we have on the right hand side the experiment with the fast cooling rate and the reproduce of the side A procedure, the experiment 45. On these two experiments you can see that we have some sponge-like shaped particles in it. A possible cause could be that we formed the solvate and then we dried off the solvent out of the solvate crystal and we get back the form B, which was the desired form, out of the solvate. We had the hypothesis that if we have a secondary nucleation, the form C was built, which is a solvate. During the drying procedure, the solvent was dried off and we built form B, but with a sponge-like shape. Because these particles are very brittle, they fall into fine particles. For a fast cooling rate, we took also a wet sample for the X-ray diffraction, and here we could really detect that we had some form C inside it, so it was a mixture of form B and C. On the other hand, we can see that the D10, so the fine particles, for the experiments with the fast cooling rate and with the experiment 45 are similar, but not the D50 values. In the next step, we kept the cooling rate constant at 6 degrees Celsius per hour and changed the seeds, that we had different particle size distributions of the seeds itself. Here you can see that after the seeding, the supersaturation goes down to a very low value and keeps more or less constant until the end of the cooling rate. And also in the FTIR we can see the impact of the seeding in a large grow of the larger particles between 50 and 150 short length. In another experiment we tested micronized seeds. These seeds got a very low particle size distribution. All the other parameters like the amount of seeds and the cooling rate were kept constant, like in the other experiments. But in this experiment we had some difficulties with the IR spectrometers, and so we had to replace the IR model by a UV model. We built up a similar model like we did before with the PLS for the API concentration on a UV spectrometer. The model was very comparable. In the graphic on the left hand side we can see that the supersaturation is only at a very low value, and we could also not observe any secondary nucleation in the FTIR. We also performed an experiment with a spontaneous nucleation at 80 degrees Celsius followed by a slow cooling rate. This experiment has the big advantage that we don't have any powder handling of the high toxic seeds. We used a supersaturated solution and stirred it for a couple of hours at 80 degrees Celsius. As you can see in both graphics, we have a spontaneous nucleation. We stirred the suspension for some longer time until the supersaturation was close to zero. Then we started to cool down the suspension. In the FTIR we can good see the increasement of the fines when we have the nucleation, and also during the cooling rate where we have the growth of the particles. To sum it up, it could be shown that if we have a high supersaturation, a secondary nucleation occurs with the undesired polymorphic form C. If we performed slow cooling rate, the supersaturation decreased. And if we used seeds with high surface, we gave the crystals more area to grow on, which reduced the supersaturation. The experiments with the slow cooling rate, this hammer millet and the jet millet seeds led to a comparable product like in the side A procedure. On the left hand side, the hammer millet micronized and the product from the spontaneous nucleation are shown. If we have a look on the graphic where we plotted the API concentration versus the temperature, we could see that we had in several experiments at the constant temperature a decreasement of the API concentration. So this shows the supersaturation area where we could run an experiment without secondary nucleation. If we take the experiments where we had comparable particle size distributions in the product, we can see that those processes run in a very comparable range from the API versus the temperature. To sum it up from a technical aspect, it can be said that IR spectroscopy and focus beam reflectance measurement are powerful tools to support the development of a robust crystallization process. The FTIR spectroscopy allows online monitoring of the API concentration and to calculate the supersaturation. The FBM could be used to observe undesired effects like secondary nucleation, and also to have a look if the crystals are growing during the process. I'd like to thank my colleagues for their contribution to this work, mainly Pirmin Hitber, who organized all the crystallization experiments, and Luca Weber and Mark Wermelinger, who ran the experiment themselves. I also like to thank Christian Lauch, which supported me the recent years for all PAT belongings.